Hello, everyone. How are we doing today? All right. I didn't realize until just now how much this was going to be in my way. All right. We'll set this down. Okay. All right. So, last time we were talking about Stokes' theorem, and I wanted to say a little bit more about it just to make sure that we're all on the same page here. Okay. Um, we have the integral on some closed contour, or closed curve, however you want to say it. All right. And if we integrate over that boundary curve, then it is the case that it's equal to the curl of that vector field integrated with respect to the surface. Okay. Now, just to make sure that everything's written correctly here, this notation is interpreted to mean this. Okay. So that dot ds, where s is bold-faced, means dot the normal vector times the surface integral. Okay. Yeah, so this here is the normal with respect to the surface S. All right, so it will change. I'm sorry, what? Yes, yeah, sorry, and I misspelled curl. I apologize for that. Just rewrite it. Okay, so we need to remember that this is a vector, so this is a scalar, and we're allowed to take the dot product of a vector and then a normal vector. That's all fine. Okay, and then this too is a vector here being dotted with this, but the way to interpret this expression computationally is like this. Okay, so this is the formula for Stokes' theorem, and what we imagine is that we have some kind of surface, all right, that sits in the plane here, or sorry, that sits in 3D space, okay, and in this environment there is some vector field, okay. I'm only going to draw the part of the vector field that sits on the surface because that's the one that's relevant to our problem, but of course there's an ambient part of this vector field as well. Okay, but we're gonna not clutter our picture with that. Okay? Stokes' theorem is saying something about the path integral around the boundary and how it relates to the curl of that vector field. Okay? So the idea is that if we are moving in a positive orientation along the boundary, okay, the thing that we're integrating is this dot product, okay? This thing is also a dot product, as we're aware, right? This is f dot, the derivative of r. That's how we interpret this one, right? Integrate with respect to t here, okay? So it's the tangent vector is what we're comparing to f. So as we move around the boundary here, if we're moving in this direction, our path is in the same direction as the vector field. Okay? Because they're in the same direction, I'm going to get a positive addition to my path integral in that region. Okay? If I move along this segment here, along that part of the path, the vector field is orthogonal to my surface. Right? I get a vector from the vector field that looks like this, and a vector from my path that looks like this, and they're at right angles to one another. Okay? What's the dot product in that case? 0, right? Okay? So over here, there is a 0 contribution to my overall integral. If I go this way, we're going to get a negative contribution because my path is in opposition to the direction of the vector field. Okay? And then down on this end, we're going to get another 0 contribution because we still have orthogonal vectors. Okay? Now, depending on how close this and this are to the same length, it may be the case that those two bits add out. Right? Most likely. Okay? What we can say about this picture is that the curl of f in here is probably close to 0, right? And if that vector field actually just is all arrows pointing in the same direction, then the curl's 0. Yeah? Another way to think about what's going on here is that if I had some object, we'll say a stick, so it's easy to see what's going on, if it's sitting inside this vector field, is the stick going to have a tendency to twist? Is it going to turn? Is it going to rotate? No, it's just going to flow to the right. Yeah? Okay. So that's what's going on here. Stokes' theorem gives us the ability to evaluate what's going on looking at the boundary to determine what's happening in the interior part of the domain. Okay? I can, by measuring the boundary, figure out a measure over the surface of what the curl's doing. Okay? So in some sense, I can get an average value of the curl by just measuring along the boundary path. Okay? And for different types of expressions, we're going to get different types of answers. So if we draw up to my ability to sketch kind of the same surface, okay, imagine we have a vector field that's kind of splitting in the middle here, right? Actually, let's not do that. We'll have it split this way. Okay, on the bottom part of the boundary, it should be blue. We're moving in the same direction, so we're going to get a positive contribution. Right? Here, both pieces, even though the vector field's pointing in opposite directions, are orthogonal to my surface. So we're not getting anything there, right? On this edge, we're going to get another positive contribution because the path of my tangent vectors are pointing in the same direction as the vector field. Okay, so the arrows are aligned, so that's a positive contribution. And then down on this segment of the path, I'm going to get 0 again because of the orthogonality thing. Now, in this case, if I have some stick that's over there, and I'll put it on this side because the picture is a little cluttered, on this end, the bottom wants to move this way. On this end, the top wants to move that way. Okay? What that's going to do is it's going to generate a rotation. All right? And we can see that in this, if we measure over the entire region here, we would expect there to be a positive curl. Yes. Yes. Yeah, that's correct. I'm keeping the example simple here, but it is true that if we have some more complicated boundary, like say the boundary was round, okay, and I'll draw all of these arrows pointing the same direction so it's easy to see, right? The tangent vectors are going to have different angles at each of these values. And so, yes, what you would do is you're taking the dot product. So it ends up being the projection of the vector field into the tangent direction. And so you get the full effect of the vector field if the tangent vector and the vector field are pointing in exactly the same direction, and then any angle between them is going to diminish the effect of the vector field. If the tangent vector is exactly orthogonal, then you get 0 effect from the vector field. And then obviously if the tangent vector is pointing in the opposite direction of the force field, then you would get a negative contribution. So yes, the angles are very important. All right. There are different versions of this picture that we can draw. For instance, we could have a version of the picture that was meant to kind of have like maximum curl. Okay, this is a straight up vortex, right? So this would have very large curl. Okay, and we can get an indication of what's going on by measuring around the boundary. Okay. Now, the other power of Stokes' theorem is that I'm going to get the same information and the same result from this integral regardless of what exactly the surface looks like, as long as they share the boundary. Okay? And the boundary and the orientation. Okay? So if I have, say, this surface here, and I imagine a version of this surface that somehow it has the same boundary. I will try to draw this as close as I can. All right, but for whatever reason, it's really bulged in the middle. Okay, imagine that bulging out towards the screen or something. All right, instead of being kind of like a twisted piece of paper or something, I would get the same answer from the problem. All right, and it doesn't matter exactly how much bulged out this region would be, as long as the boundary remains the same. Okay, it's maybe easier to see in pictures like this, to where if I have, say, a flat surface, or one that looks like this, or one that looks like this, or one that looks like this, they all share that bottom boundary. So the resulting integrals in all of these cases are going to be the same, assuming that I hold the vector field to be constant. All right, so does that clear up a little bit of what's going on here? All right. I'm going to press that button. Okay. Next up, we have our final section of new material for the semester here, and it concerns the divergence theorem. Okay. The formulation for the divergence theorem is as follows. We have a surface integral is going to be equal to the volume integral of the divergence of f. Okay. And then we can write, of course, the divergence part using the vector operator notation. All right. So we have this expression, okay, and Stokes's theorem is measuring the circulation of the vector field at the boundary of the surface. Okay, it's the tendency of the vector field to twist inside. All right. The divergence theorem is perhaps a little bit easier to understand in terms of what's going on. All right. Intuitively, what we have is, if we have kind of a similar situation. Now, this is 3D, okay, but I'm going to use not a flat example, but an example like this just to make it easy to understand. Okay, imagine that I have a vector field that's flowing into this shape from the bottom. Okay. Does it matter what shape or the exact dimensions are of this top part, this cap, for if I were to measure onto this part, everything except for that bottom, the flow? The flow through this bottom part has to equal the flow through this top part, right? Regardless of how that top part is actually shaped. Okay? That's the kind of thing that the divergence is talking about. Okay? What it's saying is that there is a relationship between, if I have some kind of solid object, all right, and I have some kind of vector field that's contained inside, okay, what I can do is I can measure the flux through the boundary, which would be the impact of those arrows on all of the surfaces of this box, or I can measure the divergence of that vector field over the volume, and I have to get the same answer. Okay? Now, if we remember the video about divergence, it was talking about the ideas of sinks and sources, right? Okay? If you are measuring the flux on the boundary, okay, basically what you're looking for is the vector field pushing or pulling on that surface? Okay? Whether or not there's going to be a push or a pull is dependent upon whether or not there is a sink or a source, or a net sink or a net source within the solid, and we can measure that by using the divergence. Okay? Does this make a little bit of sense? So I want you to think about stuff either flowing out of or into whatever the surface is. Okay? And then when we look at what's going on the boundary, we can figure out this information by either looking at all of the pushing or pulling that's being done on the boundary of the surface, or by just measuring the divergence on the inside. The divergence measures the sinks and the sources and gives me an average value, just like I got the average value of the curl by integrating over that, right? And then the surface integral gives me the net effects on the outside. So we want to find the flux of the vector field z, y, x, and we want to measure this over the unit sphere, given like this. Okay. So when the book says flux, it means the surface integral. Okay, so that's a important vocabulary word, is flux. All right. Now, this flux is related by the divergence theorem to this expression here. I guess we'll use B for ball. And so we could do the surface integral, or we can do what we will find is the much easier volume integral in this case. It depends on the cases. In general, there won't be one that's easier or harder to do. If it's a question where you're asked to use a theorem, the easier one is going to be the one that you have to switch to. Like here, we're given a surface integral problem, and then it turns out that the way to find the answer is to do a volume integral problem instead, because we're using the divergence theorem. As far as the gaming the system, that's the answer. In general, it's hard to tell. Okay, there. Just as an aside, Okay, so if I give you a problem that is, say, integrate over a tetrahedron, okay, it might be easier to do the surface integral instead of the volume integral based on the circumstances. Would be an example where one might be easier to do than the other, or it would be easier to do surfaces than the volume. It will also sometimes depend on the integrand. The vector field may be easier to deal with in one case than the other. Yeah, right. Okay, back to this problem. We want to look at what's going on here. We want to figure out the integral of the divergence here. In order to do that, we should compute the divergence. And we have the derivative of z with respect to x plus the derivative of y with respect to y plus the derivative of x with respect to z, and we get a really easy value for the divergence. It sort of. It's the dot product of this operation with my vector. So it means apply the partial x derivative to the first element, the partial y derivative to the second element, and the partial z derivative to the third element, and then add everything up because it's the dot product. So it's a notational trick. I try to write both forms to make sure that you're not confused by one of the other forms getting used in a different place. The textbook tends to use the words div and curl pretty often, most of the time. So I mix in the other notation because if you look at information that uses Calc 3 notation in other places, you're going to see the other forms too. All right. So we're integrating over the ball. We know that we're integrating 1. What is the volume integral of 1 give me? Huh? Not the answer. Tell me what quantity do I get. If I integrate the function 1 over a volume, what do I get? The volume of the body. Okay. You're not wrong. I'm just conceptual answer, not numerical answer. Now, what's the volume of a sphere? Four thirds pi r cubed, right? Okie dokie. So, relatively easy problem there. Okay. So I understand your concern. The part of the reason why that problem was so easy is that the example chosen, our vector field, ended up having a very simple divergence. Okay? And so this is one of the things that we are meant to train ourselves to pick on. If the vector field has a really easy divergence or a really easy curl, then we use our theorems that tell us stuff about the curl and the divergence if we can, because it greatly simplifies the complexity of the problem. Remember a few class periods ago where I talked about how we've kind of reached the limit of how complicated the integrals get? It's just a matter of there's more dimensions, and the way that we solve hard problems is by just making a bunch of coordinate changes. Okay. The other part of that is we use powerful theorems to do the easiest version of the problem. Yeah. Right. So, as you said, if it turned out that instead the divergence was, it doesn't matter what constant it is. If it was just a constant, then we'll say it 4, so it's an actual number. The integral that we would have gotten would be the integral of 4. We know that we can factor out numbers, and this is a volume integral. Okay? That's why this example is in here, to remind you that volume integrals and area integrals, if you know what the area of, if you have a nice domain and you know what the area is or you know what the volume is, you write down the answer. Okay? There are some problems where the trick to integrating them is to keep doing coordinate changes until you turn it into a volume integral. And then you just have some constant, which is the number, right? And then you multiply by the volume, and the problem's done. But yes, this is something to be happy about, not upset about. We like it when the problems are simpler. But I understand why it can be concerning. All right. Let's do another example. A very important one for theory. All right. We have previously talked about the idea of an electric field. Okay. Now, as a reminder, there's a force field version of this equation. That has a lowercase q. All right. It is convention when we talk about electric field problems to divide by the lowercase q. It is a so-called test charge. All right. And so what you imagine when you write down the equations for all of this stuff is that you have q, which is usually thought of to be the charge of an electron being the test charge, sitting in space at kind of every point, and the electric field tells you what the influence is on that test charge. Okay. So Q is the charge at the origin. And X is a position vector XYZ. We want to use the divergence theorem. To show that the electric flux through any closed surface containing the origin is equal to this. All right. Now, the problem is that we're not allowed to say anything really specific about S. Okay? S is any closed surface. All right? I imagine everyone's probably thinking about a sphere, all right? But it could also be a cube, all right? Or some other kind of oblong shape like something weird like an hourglass or a pill shape or whatever, all right? Anything is allowed. So what we have to do is be able to say other types of things in general. So what we want to do is we're going to make a small sphere of radius A that's going to be centered at the origin. Okay? Now, the reason we make this change is because this is something that we can say something about. And so we can say that the integral over S is equal to the integral over S prime plus this divergence. Yeah, give me a sec. I was about to mention that. So the reason that we're allowed to say this is because we know that the electric field has this formula. Okay. The divergence of the electric field is 0. Okay. It's actually one of the exercises. I don't know if I assigned it or not, but it is an exercise in the textbook to verify this. Okay. But we can add this because it allows us to add 0 to what's going on. All right. And the the E here basically is okay. So let me explain this a little bit more carefully. Here we have S. Okay, we are using the divergence theorem to write the second line. Okay, basically what we're doing is we are replacing the. I'm imagining that E is make sure that I don't say this wrong. I have a volume that is bounded by S. Okay, so there's one of those weird shapes that I was drawing. Okay, it doesn't really matter what it is, but I have a shape that is bounded by S. Inside of this, I have an S prime that's a tiny circle that's sitting at the origin. Okay, so what we're doing is E represents the part of the surface that's outside of that boundary, and by the divergence theorem, the divergence in that region has to be 0. Or by sorry, By the divergence theorem, the sum of these two things has to be equal to this. Because I can imagine this as being the tiny volume in here, but I use the divergence theorem to replace the volume integral with a surface integral. Okay? And then I have the leftover volume. The reason it's not more complicated is because the divergence of the electric field is 0, so this goes away. That's the trick. Yeah. Right. Well, that's the thing is I have a big surface that I don't know anything about, right? But I can make a as small as I like tiny sphere that includes the origin that sits within that other surface. Okay? And so I do that because it allows me to, by what I just explained, ignore the actual geometry of whatever the more complicated thing is. So, because this yeah, I'm to to use the vocabulary that you just used. I'm making a much smaller Gaussian surface inside the Gaussian surface that I have in order to get rid of however complicated the outer surface is. Yeah, that's the backwards part of this from the people who are a little bit familiar with this kind of idea from a physics class. Is we always pick spheres because spheres are the easiest, right? But we're not picking a sphere outside of the charge distribution. We're picking a sphere inside of another surface. Yeah. All right. Okay. So what we have now succeeded, I hope, in explaining is that all of the information that we care about happens on the boundary of the tiny sphere. Okay? This is a very easy thing for us to write about. We can use our notation switch to replace s dot ds with the norm dot ds not bold-faced. Okay? And we know stuff about the electric field and the normal vector. The electric field we have a formula for. It's EQ over this. And we're dotting it with this because this is the normal vector on the surface of a sphere, right? It's just the position vector made length 1. I'm going to need a new page here. So we have this expression. We can continue to work on it. And then x dot x is going to be this, right? So we're left with just the length of the position vector squared here after those quantities divide out. We know that the sphere is radius a, so we can replace the length of the position vector with a. And we've reduced the integral to this. All right. Everything inside there is a constant with respect to the integral. This, as we had in the case earlier, where we ended up with just a volume integral, this is a surface area integral. What's the area of the surface of a sphere? I will let you know, now that you're Calc 3 students, so we've gotten to this point in the semester, this is one of the ones that you need to memorize. 4 pi r squared is the area of a sphere, the surface area of a sphere. And we have shown that the flux through the boundary of any closed surface where the charge is concentrated at the origin is given by 4 pi epsilon q, where epsilon is the permittivity constant. Most people just call it, I guess, the electric constant. But I always liked, if you flip open a physics textbook, it has this really, what's the right adjective? I'm hearing my mother's voice in my head, so I'm just going to go with hoity-toity, I guess. The permittivity of free space, and then the magnetic constant is the permeability of free space. Seems a bit of a mouthful. Anyway, pretentious. That was the word that I was looking for. All right. So, for those of you who have done physics stuff, I'm sure that particular little formula has come up quite a bit as the result of these Gaussian surfaces problems that some of you mentioned. Have plenty of other types of examples here. All right, so we have reached the end of the new stuff. Okay, I know that in the last couple of sections we've introduced some kind of complicated formulas. All right, it takes everyone a while to adapt to these things. All right. So it is my recommendation that you go through and do the exercises and use this as an opportunity to practice up on your integration skills, getting used to these things, the notation, and all of that. We have two, because Friday is the designated study day for the university, class periods next week in order to go through ideas and review. Our final exam, which is going to be the focus of our study, is going to be mostly about Chapter 16, but due to the nature of Chapter 16 kind of subsuming the rest of the material for the course, you should treat it like a comprehensive final that we're preparing for, okay? Most of the questions will be inspired from ideas from Chapter 16, but we're going to be using all of the skills of the semester, okay? We will have the same rules for the exam in terms of having the formula sheet type things we've had in previous exams. I'm not going to take that away on the final when we've had it for the rest of the semester, but it's the same rules. No worked problems. They're basically just formulas and reminders about how to set up certain things. But there's a lot of stuff to remember, like the formulas for gradient, divergence, and curl, and many theorems now, right? Those kinds of things, so no issue with that. But we'll start working on all of that. We will talk about skills that you need to make sure that you're sharp on for the final, as well as some of, but not all of the things that are guaranteed to show up on the final exam in terms of problem representation and stuff. You'll know most of it. I reserve the rights to not explicitly tell you about a couple of things but you'll get some strong hints. All right, so take care, have a good weekend, and I will see you next time.
Thank you.